Hi, it's Mr. Zachary. Here are the solutions for questions 6 through 10. 6 starts with a modified Atwood machine. We attach one box to another box by a string. If you wanted, A asks if you wanted to add 10 grams to 2, how would you keep the total mass the same? Well, if you add 10 grams to 2, then you need to take away 10 grams from 1 to keep the total mass the same. Let's say this had a mass of 50 grams, this had a mass of 50 grams. If you make this one 60, to keep the total mass the same, you need to make this one 40. So keep the mass the same by adding 10 grams to 2 and subtracting 10 grams from 1. Part B asks if you added 10 grams to 2, what would the system accelerate quickly or not as quickly? The way to think about this is that the force of gravity, because you've increased the mass here, the force of gravity for 2 has gotten bigger. And since the force of gravity has gotten bigger, the whole thing is being pulled by a bigger force. But you've kept the mass the same, and so now you have a bigger force pulling the same mass. And as we know, when you increase the force, you increase the acceleration if the mass is the same. For question 7, block has a mass of m and acceleration of 3. Here's the picture. A asked the picture if we connect two identical blocks glued together and pulled by a string. We'll draw the picture and the force diagram for the situations. Here's the picture for the one block. Here's the picture for the two blocks. Here's the force diagram for the one block. The string is pulling, the force of gravity and the table are pushing. Here it is for the two blocks glued together. You can treat them as one object. So the string is still pulling. The force of gravity is bigger now. It's twice as big. And the force of the table is twice as big because you have twice the mass. For part B, what will the acceleration of the two blocks be when they're tied together? If one block pulled with this force has an acceleration of 3 meters per second every second, if you double the mass, keep the force the same, the acceleration will be half as much. Here's an example using some numbers. If we assume that the block has a mass of 1 kilogram, and that's fine to do, you can use numbers that will fit the situation, kind of make them up on your own. But mass of 1 kilogram, that means that for the one block, it has an acceleration of 3 meters per second every second. So the force we're pulling with is 3 newtons. If we keep the same force, 3 newtons, but double the mass, 2 kilograms, what's the acceleration? Turns out to be half as much, or 1.5 meters per second every second. For question 8, free fall. What's the definition of free fall? Free fall is defined as this, that the only force acting on the object is the force of gravity. Could be moving up, could be moving down, could be moving sideways, we don't know. The key point is that the only force is the force of gravity. For B, situation where something's truly in free fall. Because of air resistance, nothing except in really science experiments could be really be in free fall, because there's always going to be some air resistance. Sometimes the air resistance is so small that we can neglect it. It's almost like a rounding, that it won't show up in our rounding. Like in this case, if a ball is dropped in class, it'll have very little air resistance, and so we can treat it basically like it's in free fall, even though we know that it actually isn't. And here's the force diagram for it. That's C. For question 9, if I'm looking for the weight of something, that is the force of gravity on it. And we know that the force of gravity can be calculated by the mass of the object times the acceleration of an object in free fall, 10. And so the weight of this is the weight, so the nickname for that, is 3 times 10, so it's 30 newtons. Do the same thing with the others for their weight. The force diagram for it think about what's touching the cat. The person is in contact with the cat, and so the person is pushing up. Gravity is pushing down. The stool is not in contact with the cat, and so it does not exert a force. Find the weight of the stool. You do the same thing. It is m times g. Mass is 5 kilograms, so the stool's weight, the stool's force of gravity on it, is 50 newtons. Here's the force diagram. Think about what's touching the stool. The person is touching the stool and pushing it down. The floor is pushing it up, and gravity is pulling it down. We know it's not accelerating, so we know that these two forces together must combined add up to that. So if that one is 7, that one is 3, then this one must be 10. Finally, C, finding the weight of the person. The mass of the person is 60 kilograms, and so the weight of the person is 600 newtons. Once again, what's touching the person? The cat is pushing down, the stool is pushing up, and gravity is pulling down. Now, the person isn't touching the floor, so the floor is not pushing on the person. And finally, number 10. You have 4 rubber bands stretch one to produce amount of force F. You want to produce twice as much force. You can stretch 2 rubber bands, each that same stretch, let's say 5 centimeters, and 2 rubber bands will give you twice as much force as 1 rubber band. If you pull with only 1 rubber band, but you stretch it twice as far, you'll produce twice the force. And if you use all 4 rubber bands and stretch each of them only a quarter as much, then you will only produce a quarter of the force, but you have 4 of them, so overall you'll still produce the same force. You can combine these in any way, but the idea that you can combine multiple rubber bands to get the same force, or you can stretch the rubber band different amounts to get more force.